Thank you. So this is going to be a talk along your previous talks of the day on the astroparticle physics. And the front page essentially shows that we have this beautiful night sky and we get all kinds of detectors in space, on ground, underground to detect all kinds of signals. And the focus of this talk is going to be the cosmic particles and using them to study the universe. Okay, so I'm sure this concept has been brought up many times during the day and during the workshop, but essentially the multi-messengers are this new concept gluing together 4 different types of waves and particles, including the electromagnetic radiation, cosmic rays, which are, so electromagnetic radiation are essentially photons from all wavelengths, all the way from radio to gamma ray. And cosmic rays are charged particles, so they will not travel in a straight line, but instead they are confined by magnetic field and they go through strong interactions. And the neutrinos, which essentially is a neutral particle, so they can travel without delay. And they usually go through weakly interaction, so they barely interact through cosmological distances. And the final one is the gravitational wave, which tells us a quite different aspect of the compact objects. And then in my title, I specifically define the cosmic particles, which refer to the high energy photons, cosmic rays, and neutrinos that are produced by extreme activities of the universe. So I'm going to use the 4 different colors indicating the 4 different type of messengers and try to, using this little time to show 2 main subjects, which are different combinations of different messengers to show how powerful in high energy astroparticle physics, where we combine different messengers, we can learn many different stuff. So the 2 main subjects include the hunt of the PeV proton accelerators inside our own galaxy, the so-called pevotron. And the second topic is the understanding the origin of the cosmic neutrinos. Starting from the first one, I see there's a lot of people in the audience from the cosmology and more broad, like slightly different from the astroparticle perspective. So let me start from where everyone is comfortable with. So this is a intensity map for the electromagnetic radiation background, all the way from radio, this big CMB, well, EV is what human eyes are sensitive to, and 1 TeV is essentially comparable to the kinetic energy of the wing when the bee is flying. So the CMB is, everyone, you are experts about this origin of the CMB, and the distant infrared and optical emission comes from distant galaxies and stars. When we go to higher energy in the X-ray and the gamma ray band, we started to see the active galactic nuclei and starburst galaxies. But the cosmic particles comes at even higher energy. So the left-hand side, when I switch from frequency to electron volts and move even higher from so supposedly I'm going to do an extension of the left plot to even higher energy. That's what has been measured by the recent satellite and ground-based gamma ray detectors. It would look like this. So first of all, entering the sub-GeV to TeV regime, this is our TeV friend, you would start to see that the intensity is continuing as shown by this red data points. This is measured by the Fermi satellite, which is a full sky satellite that sees the full sky emission in gamma ray band in between sub-GeV to TeV. This is the, someone has already raised a hand. Should I answer that, or do we wait until the end of the talk?
I can ask quickly, actually. In the plot,
sure.
You'd plot on the frequency versus luminosity. You show the radio, right? And radio
yes.
goes, like, do we know that this radio goes through that? Because it seems like it's under the CMB, right? CMB is like, is it, you mean synchrotron like radiation for radio or something else? You mean, what do you mean by pink color?
Yeah, so this pink color is more like an estimation about the radio background So there was a balloon-borne experiment that detected a diffuse radio background that stands above with a temperature different from the CMB. And that is but the origin of that radio background, as far as I understand, is still unknown.
Okay, and does it reach up to 10 to the 11 gigahertz, or just because it goes up to from figure, it goes to up to 10 to the 11? Is it just rough plot, or?
This is a very rough plot. It's purposes for indication.
Okay, so we don't know after gigahertz more or less what this guy does, right? Or 10 gigahertz. We don't know surely because it mixes with CMB.
No, it's not surely known. So the balloon-borne experiment I mentioned is more of measuring a portion of the sky and but they do find a signal that's different from the CMB, and they even have a specific anisotropy pattern.
Okay, I just want to ask that. Thank you.
Sure. Okay, so if we move on to higher energy, then the diffuse, so all of these are diffuse emission, meaning these are emission when you already get rid of the point sources. So the red data points is indicating the diffuse gamma emission from the Fermi observation. And on the right-hand side, by the way, can people see my cursor? Not really. The pointer, can people see my pointer?
I can't see it, sorry.
Oh, you can't see it?
No, I cannot.
Okay, never mind. Then I just speak. So the plot on the right-hand side is the sky map measured by Fermi between 0.1 and 100 GeV. So this is a big, this is the full sky emission, meaning you can see there is a very bright galactic plane in the center, in the middle, and on the above and below the plane, there are many bright point sources. These are actual galactic sources. Most of them are blazars. So the red data points I show in the middle plot is essentially the diffuse gamma emission that is left over after subtracting or removing the point sources from the Fermi full sky observation. And this emission has this diffuse emission has so far been understood as mostly coming from the blazars and radio galaxies in the highest energy, and from star-forming galaxies at 10 GeV also, or below 10 GeV. And when you go above that TeV energy, there are two reasons that the observation is getting harder. The first is that the spectrum, as you can already see from the Fermi band, is going down. It seems to be cutting off, or the power loss spectrum make the flux even lower. And also with the energy of the photon going above 1 TeV and higher, they would start, especially above 100 TeV, they start to interact very quickly with the CMB and any infrared photon of the universe. So that means these TeV energy photons, or photons essentially above TeV, would be attenuated by the actual galactic background lights. So that's why the observation switched onto ground-based detectors, simply because you cannot put a payload that's much, much bigger than Fermi in space. So the ground-based gamma detectors in TeV regime consists of two big groups of detectors, which is different by the techniques. One of them is called the IACT, stands for the Imaging Atmospheric Cherenkov telescopes. So these are individual mirror-like telescopes where they measure the primary air showers when they get into the Earth's atmosphere. Another type is called the air shower detectors. So these are ground-based water tanks. It's usually water tank array. So they can, instead of seeing the primary Cherenkov shower, they would see the secondary emission when the air shower generated and producing a bunch of secondary showers. And when they arrive to the ground, you can see the footprints of this shower. And then you track back to see where the initial photon comes in. So both of the detectors are currently operating. The IACTs include the Veritas, the HASS, and as well as MAGIC, and the air shower detectors at the highest energy include the HAWK, the TBAT AS gamma, as well as a LASSO calibration. So on the right-hand side, the second middle plot is showing the full sky emission observed by a South Pole sky is about two-thirds of the sky emission by the Hawk Observatory. So you can see that there is, and this way is in the equatorial plane coordinate. So, but nonetheless, you can easily see there is a bright plane at the center indicated in between this white dashed line, and that in between those sources, that's the galactic plane, and you see most of the sources on that plane. And above and below the plane, there are only two extragalactic sources observed at this energy between 0.1 and 100 TeV or so. That's the two Macarians, that's Macarian 501 and Macarian 421. All right, and then there's lately another publication by LASSO collaboration at even higher energy above 100 TeV. And there you can see, so it turns back to the galactic coordinate again on the third plot. And you can see there is 12 bright sources being seen from the galactic plane again. And that suggests that the galactic plane is really a very powerful place where you can see photons up to above 100 TeV from them. Now that the even higher energy, we can also using the water air shower Cherenkov detectors to observe these gamma rays at even higher energy. But at such high energy, meaning above 10 to the 9 GeV or 10 to the 18 electron volts, the photon energy is so high that they ended up producing a very big footprint. So your air shower detector has to be separated with larger distances. So Pierre Auger Observatory, which is mainly a cosmic ray detector, has also been measuring the ultra high energy photon observation. So far, there's no ultra high energy photon being detected, and the upper limits is indicated by the red arrow right below the Auger picture. Okay, so these are brief summaries about the current understanding and detection of the highest energy universe in photon. So to fully understand the galactic sources, let's brought in the other messenger, which are the cosmic rays. So the cosmic ray flux, as probably the plot has been shown earlier, but the y-axis is the scaled flux with the flux of the cosmic ray multiplied by e to the 2.7 to shrink the y-axis. And x-axis is the energy of these cosmic rays, and our B friend is on the left-hand side. The center of momentum energy made from man-made accelerators is marked roughly out there, and the highest energy particle that has ever been detected reaches above 10 to the 20 electron volts. So that's roughly the kinetic energy of a baseball. Even though we have been working on this for a long time, I still feel amazing to think like the baseball composed of more than 10 to the 23-ish of atoms. And if you compress all of them into one, that's the particle you get from the universe, how energetic that is. Right, so the spectrum measured all the way from the TeV to 10 to the 20 electron volts has been shown in this plot, summarizes in this plot from measurements by many different experiments over the decades. There are two main features. One is the so-called the knee feature. That's where the happens around 10 to the 15 electron volts, where the spectrum you can see from e to the minus 2.7, because my y-axis is multiplied with e to the minus 2.7, is switching into something softer, like e to the minus 3. So there is a turning of the spectrum, which suggests that there might be a reason that this could be a place where the galactic cosmic accelerators stop and switch into something else. And another feature is at around 10 to the 18.5 electron volts. That's the INCO of the cosmic ray. And this is where the actual galactic sources for sure comes in. So the first part of the talk is going to focusing on the papatrons. So specifically, the large amount of the hard spectrum hadronic cosmic ray sources around the INCO. Because the detection of the knee in cosmic rays, we know that these must be hadronic. There must be a lot of hadronic sources, and these sources needs to be there confined in a galactic magnetic field to produce the emission of cosmic rays in the knee. But these emissions, these cosmic particles, would interact with the gas inside our own galactic plane in our own galaxy. So that is going to producing a neutral pion, which quickly decay into gamma rays. But these gamma rays somehow are not seen in the gamma ray sky. And so far, there have been very limited number of papatrons being identified. That include the hadronic supernova remnants detected by Fermilab, the specific two IC443 and W44 with the pion decay feature at sub-GeV. There's also the galactic center papatron that was detected by HASS. That is a central molecular zone and a emission zone that's very close to Sagittarius A star and seems to be giving also a hadronic feature. But other than these two sources are far from enough in explaining this big cosmic ray energy that has been observed. So where are the papatrons? The latest observation from all of these very high energy gamma detectors has luckily found more potential PeV cosmic accelerators. And this includes the one already shown, the Galactic Center, and plus some interesting new sources like a Microquasar that was detected by Hawk, a Cocoon, which is a stellar cocoon detected by Hawk in a different area closer to the edge of the plane showing on the top. There is recently a supernova remnant being detected by TBAD that's suggesting, and then a few other very high energy gamma detectors suggesting that this could be a site of hadronic emission. There is also the Crab Nebula recently being reported by LASSO to shine above 10 to the 15 electron volts. Although the Crab Nebula looks consistent with an electron emission all the way from synchrotron band to the inverse Compton, with inverse Compton extending all the way to PeV band. So in the next few slides, I'm going to walk you through several of the new papatron sources, starting from this Microquasar. So this is a sub-PeV gamma emitter, and the Microquasar, its SS433 is has been known from back in 90s and 80s even, that this is a X-ray binary. And the red dot at the very center is the X-ray binary itself, which consists of a 10 solar mass black hole and a 30 solar mass donor star, OB2 type of donor star. And the sky is very tiny, but it puts out a very gigantic jet, as shown in the bottom. A big jet that's passing through the supernova remnant surrounding it, and the remnant in this color on the top plot in different color is this fish shape of nebula called W50, and this nebula, the head and the tail of the nebula has been already shown in the X-ray band, as indicated by the black curve, the black contours in the bottom plot. That's the X-ray emission of the big jets from the X-ray binary. Now with Hawk, we were able to identify point-like TeV gamma rays in both lobes, as indicated by the colors in the bottom plot. And this is quite an interesting observation for two reasons. The first is that we detected the gamma emission above 20 TeV from this source. And this source is the orientation of the jet is perpendicular to the line of sight. That suggests that and also the speed of this jet is only subrelativistic. It's only a quarter of the speed of light. So there's barely Doppler boosting in this source. And the 20 TeV photon we see have to be emitted by electrons above 100 TeV. So electron acceleration is typically very difficult when at very high energy. The reason is simple, because they radiate very quickly in any magnetic field with synchrotron radiation and curvature radiation. So to make electrons up to such a high energy by a mildly relativistic jet is quite impressive, but somehow it's actually challenges some of the existing acceleration theory, but somehow we see them from nature. And the second reason that this is quite interesting, very high energy gamma emission observation, is that the gamma emission we see is not coming from either the bottom of the jet close to the X-ray binary or close to the E3 and the W2 region where the X-ray jets is interacting with the interstellar medium, the head and the tail of the supernova, the remnant. But rather the gamma emission is coming from some intermediate distances inside the jet, close to the E1, E2 X-ray emission point inside the jet and the W1 on the western lobe. So this suggests that the particle acceleration site must be at least 30 parsecs away from the hole. And this is this is essentially the first time that a set of very high energy gamma emission jets has been resolved at this high energy. So it's quite informative that the particle acceleration site happens to be somewhere inside the jet, not close to the region where magnetic field interaction is strong. So we said that we look for the hadronic pevitrons, but it turned out that the SS433 looks more like a leptonic sources. The reason is when we put together the radio, the X-ray, the TeV gamma ray, as well as the GeV gamma ray emission from this source, we find a relatively consistent picture that the emission can be explained by an inverse Compton emission by relativistic electrons that cool very efficiently. It can hardly be hadronic source because this is a region with does not have a strong gas distribution. And we already know the kinetic power of these jets. So to make these jets shine in to produce enough flux that the gamma ray observatory has been seen, we will need to almost 100% of the jet power to accelerate proton, which is very difficult. So that's why the hadronic scenario is disfavored in this case. But nonetheless, this is quite an interesting electron PeV accelerator. Now, the second source I want to show you is another type of new surprising pevitron source, which is the Cygnus Cocoon. So on the top, this is the beautiful Cygnus constellation with stars not really related to each other. But at the very center is the Cygnus Cocoon. So the Cygnus Cocoon is a 2-degree radius cocoon composed of a bunch of stellar clusters as indicated by the white dots, cluster dots on the plot on the showing on the top. So these are essentially young OB2 stars. These are regular stars, and they're producing wind surrounding in that region. And in the infrared band, the plot on the top is showing in the infrared emission from that region, from the cocoon. So the infrared emission shows that there are gas distribution in that region, and there is a clear boundary, which is indicated by the blue color in the top plot. There's a clear boundary from this gas infrared emission, showing that the wings of the stellar clusters is inflated a cocoon-like structure that is shining. That's shining in the infrared band. So Fermilab was able to detect a GeV gamma emission from that region, and the flux of the GeV emission is so high that they cannot be explained by these zombie cosmic rays that has been staying for millions of time in this region, but rather by some freshly accelerated cosmic ray in that region. So then the bottom plot shows the TeV emission that was observed by the Hawk Observatory. And we find that the TeV emission indicated by colors is very spatially consistent with the emission detected by GeV, as indicated by the blue contour on the bottom plot, as well as the infrared emission as the color on the top plot. So this suggests that this GeV to TeV gamma emission both trace the infrared emission and is associated with this particular cocoon. So above 100 TeV gamma ray was observed from this region as well. We find that the gamma ray emission are very likely coming from the PeV protons accelerated by the stellar winds. On the left-hand side, I am showing a spectrum fit for the GeV and the TeV gamma ray data from this region for two scenarios. One is a continuous injection of the sources in this region, and the second is a recent burst happening from the in a stellar cluster and producing particles that coming from higher energy but escape the region slowly. So both of the model would explain the TeV gamma emission very well. While on the right-hand side, I am showing a spectrum from a leptonic scenario where the electron emission was assumed to explain the GeV to TeV emission. But in this case, you can see that the gray color is indicating the leptonic emission. And in this case, the electron have several difficulty in explaining the source. For example, it cannot explain the GeV to TeV emission simultaneously. And also because of the huge display of the gas, the gas in this region, the Brandstrom emission of this relativistic electrons would be so high that it would already overwhelm the measured sub-GeV observation by Fermilab. There's also no X-ray observation being seen from this region as well, which confine the synchrotron emission of this electron. So that's why we confirmed that we concluded that the Cygnus Cocoon is very likely a GeV, a new type of pavotron. And this is a very surprising type of a pavotron, because normally when we think about particle acceleration, we would go to the kind of neutron stars or black hole jets, those very extreme compact objects. But in this particular case, these are ordinary stars, and these are just wings from regular stars that has already been so impressive. Okay, so for that, I would summarize this, what we have learned so far with this all efforts from the very high energy, the new generation of very high energy gamma ray detectors. We have seen many new types of sub-PeV emitters, and that includes some surprising type of emitters. And this is still incomplete and far yet from explaining the real need that we have seen in the cosmic ray band. So this is remaining a underpopulated pavotron zoom, and future work will be needed to understand this difference between the gamma ray and the cosmic ray sky. Another interesting thing is that I have mostly focusing about the point sources, or the sources along the galactic plane, and told you that we do not see individual sources. Nonetheless, we do see a galactic diffuse gamma ray background. So these would be the diffuse emission coming from the hadronic cosmic ray interacting with the dust, but for a long time. So they already leave the original source location and showing up as a diffuse emission. So this is the sub-PeV galactic diffuse gamma ray background observed by the TBAT AS gamma, reported earlier this year. So on the left-hand side, this is their full sky map showing the red data points are the photons, sub-PeV photons observed from the galactic plane. They also see some emission from high and below, which are cosmic ray background. So after comparing the background and the signal, they concluded that there is a firm detection of the diffuse background, and shown from the right-hand side from two sky regions with the red data points indicating the flux of the diffuse gamma ray background above 100 TeV. So this is now when I would bring in a new messenger, the neutrino messenger. So we know that the diffuse gamma ray emission is coming from hadronic cosmic ray interaction, but the same hadronic interaction is also going to producing charged pion, as we had discussion yesterday. This charged pion would quickly decay into neutrinos. So we see these gamma rays, that means we would be able to see the neutrino count. There is also a neutrino counterpart in the sky. So the firm detection of the diffuse gamma ray background would predict a population of the neutrino emission. Well, there are several ways to derive this neutrino population. You could start off with the cosmic ray, the knee observation, as I showed earlier. But from the cosmic ray to neutrino, there are different complications. For example, the distribution of the sources, spectrum of the protons from individual sources, and the composition of the cosmic ray. It's not only proton, there's also helium and higher elements. So all of those complications would brought in big uncertainties in the prediction of the neutrino flux from the galactic sources, from the diffuse galactic plane. And that's why we used instead the detection of the diffuse gamma ray flux to derive this neutrino flux, because neutrinos and gamma rays in this case are counterparts produced by the same parents. Even there are uncertainties in the parents, the children come from the same processors, so they should be alike. So that's why we used the gamma ray flux and derived the neutrino flux shown on the plot on the right-hand side. So this is a very complicated plot, but essentially the prediction of the galactic plane emission is shown by the purple color, shaded color. And this is consistent with the upper limits that has been posed by the IceCube and Antares observation of the galactic plane, as indicated by the cyan or light blue dashed color. But in the future, it says it's not very far away from this upper limits. And that suggests that these diffuse emission should be able to be detected by the next generation experiments. Okay, so that concludes the first part of my talk, which is about the hunt of the pavotron sources. And you already see that to understanding these pavotrons or PeV cosmic ray accelerators, as well as the knee feature in the cosmic ray sky, we would really need some coordinated observation and analysis. So I'll try to go to the second part unless we have some immediate question for the first part.
Questions? Do you care?
Okay.
No questions at the moment.
Okay, cool. So I'll just proceed to the second part, which I'll try to quickly summarize a bit about the understanding of the cosmic neutrinos, the origin of the cosmic neutrinos. So this is, again, trying to start from the what audience in this room are comfortable with this big summary of the cosmic neutrino background. The y-axis is the flux, the differential flux in this case from neutrinos, essentially the neutrino background from the universe. X-axis is a gigantic x-axis, cover more than 25 orders of magnitude, and our B friend is out there. So from lower end is what you talked about yesterday about the cosmological neutrinos that has a big impact in the formation of the large scale structure, but not yet detected. In the MEEV band, there are detections from the neutrinos, and KEV band neutrinos from the sun and from the supernova remnant burst. And at the highest energy, there is a prediction of the pre-existence of the cosmogenic neutrino, which are neutrinos produced when the cosmic rays above the ANCO interact with the CMB. This is a population of neutrino that has been predicted to exist because we see both the cosmic rays and the CMB, but we have not yet seen this population of neutrino yet. And this is a very active experimental frontier for the next generation detectors to pursue. Now, the major advances in the high energy neutrino observation, which has already been talked earlier, is the population of the astrophysical neutrino. So this is the summary. This is a quick summary plot of the diffuse neutrino flux that has been detected by IceCube. There are different ways to identify these neutrino events, but generally they are consistent with each other, and the population of this astrophysical neutrino flux stands where above the atmospheric background, above 100 TeV, which is establish the existence of the high energy all sky neutrino flux. Though the source of the bulk of the observed neutrinos are unknown. So let's go through a little bit of interesting facts about these neutrino sources. So first of all, these neutrino fluxes detected by IceCube happens to happen with a flux that's comparable to the cosmic diffuse gamma ray background detected by Fermilab that we talked earlier, as well as the ultra high energy cosmic rays that other speakers has been mentioned today. So this could be a pure coincidence, but that could also indicating some interesting common scenario that's explaining all the three types of messengers. The second surprising fact is that although we do not know the sources of these diffuse neutrinos, the sources must be very abundant and powerful. And this is a plot to show why this is the case. So we thought about the shock power transients as the sources of neutrinos. The reason is we know from the cosmic ray sky, the shocks are very promising sites for particle acceleration. And there are a lot of transients that's powered by shocks. So we compared these optical transients and their energetics, as well as the ability of their acceleration to the observed neutrino flux. So specifically, the y-axis here on the plot in the middle is the optical power carried by a set of optical transients, and x-axis is the maximal energy that can be produced by the shocks at the peak time when the optical luminosity, the light curve is at the peak time. So the maximal energy is a bit tricky because the optical transients at their brightest phase is usually having a shock that's in the radiative regime. So it's not as high as what a adiabatic shock that would be, because the layer that's the ionized layer is rather thin. So we computed the maximal energy and the energetics of the optical, and using the energies of the energy emission rate of the optical transients in the optical band as a reference to the shock power of these transients. We considered a bunch of different type of transients, all the way from TDEs to core collapse supernovae as a whole class, as a conservative comparison, as well as a few very bright, the population of the luminous and fast optical, the FBOT, as well as the superluminous supernovae. So we can see that the optical power carried by these transients, as indicated by the silver solid line with an upper arrow indicating epsilon relative smaller than 100%, that is the energy, assuming that at least 100% of the that's the 100% of the power of these optical transients, assuming they have this population extending to cosmological distances. And on the top right, that's the ice cube diffuse neutrino flux. So it's only when the power of the cosmic rays is only when the optical power, or rather the shock power, putting 100% of the shock power into the cosmic rays, that you can still not explaining the diffuse neutrino flux that's observed by ice cube. So that suggests that this exercise suggests that the sources must be something more steady, longer term, as well as more powerful, as well and abundant, because there's no anisotropy observed from these neutrinos. Right. So, and finally, the sources seems to be opaque to GeV gamma rays. There is already there are several sources that has already been measured by the IceCube Observatory at a 3 sigma broad line level, and these sources, including the NGC 1068 showing on the bottom, seems to have a very bright neutrino flux, meanwhile a relatively low gamma ray flux, or some of them does not even have gamma ray flux. So this is another interesting fact, that these sources seems to be opaque to the GeV gamma rays. So what kind of a monster would be satisfying all these conditions to make these neutrino sources? So in this final bit, I will quickly show a model that we made to explaining these neutrino sources. This is just one of the model. There are many other models out there, but the model I'm going to show is a model from the neutrinos from the jets inside the galaxy clusters. So we know that we commonly see the gamma ray very high energy jets inside, that's the AGN jets, but these jets are usually sitting in the very dense core of a galaxy cluster. So inside the galaxy cluster, you have the magnetic field and electric magnetic energy converted into particle acceleration. And when you get accelerated, you're not going to leave. You're instead confronting a very thick environment with all types of different interaction channels, depending on the species and energy ranges you have. So what happens at each interaction is a lot of interactions and secondary productions. So you would need to consider all of the secondary emissions, because on the right-hand side, I'm showing a case that had you only considered the primary neutrino emission from the first vortex, you would see a very different spectrum that from the observation, something like really hard spectrum. But when you consider the secondary emission, essentially all the children particles from higher order interaction, that would showing up usually at the lower energy, but drastically change the spectrum you observe from the entire source and make it much closer to the observation. So we set up these numerical simulation to account for these secondary emissions. Specifically, we put up a intercluster medium gas that follows the classical beta model observed by X-ray emission, suggested by X-ray observation, and putting up a radiation background coming from the galaxies as well as the distant infrared emission. We have a magnetic field to let the particle propagate through a homograph type of turbulence. So here is a quick movie showing the particle trajectory in this intercluster medium for a particle at an energy above 10 GeV at 10 GeV. So in this case, you can see that the particle would gyrate very quickly in the center, but it quickly goes out of the galaxy cluster with a total duration of only less than 50 megaparsec, which is very small compared to the age of the galaxy cluster. So in this case, this cosmic proton would just get out of the source without any interaction. In the second movie, this is a cosmic proton that has 100 times less energy. So this is going to take a long time for them to get out, and it's actually the primary particle indicated by blue never get the chance to leave the source, while the secondary particle produced by the primary proton particle and the secondary indicated by green was able to, there are a huge population of secondary being produced, and they, because of the whole confinement of the longer confinement and the more number of particles, neutrinos was eventually produced and leave was quickly getting out of the system. So when we put together all of those emissions, including the cosmic rays that comes out from the first movie, the ones that leave without too much interaction, as well as the neutrinos produced from the protons or other cosmic ray particles, showing in kid scenarios in the second movie, producing these neutrinos into intermediate energy ranges, as well as a gamma ray flux that is produced simultaneously with these neutrinos. We find that this scenario would be able to produce the diffuse gamma ray, neutrino, and cosmic ray all at the same time. And this is able to explain this coincidence that all three messengers happen to have a similar energy flux. So that's just one scenario, but there are it's an interesting scenario that happens to explain this coincidence. But the key point I want to say is we do need the numerical study to understand the source physics and the observation. So I think that concludes my talk. I think I'm right at the time mark. Thank you.
Thank you very much, Kia, for this nice talk. Any questions from the audience first? Federico, please.
Just a simple question, like when you're looking for the PV, the pentatrons, how far do you expect them to be? Like how far do you look?
So it's mostly galactic plane. So it's no more than tens of kiloparsec. And in fact, most of these pentatrons I show on this page is coming from very nearby distances, a few kiloparsec. And that supernova remnant out there is only at 800 parsec. That's why so that already tells you why we didn't see them earlier, because the emission is not very strong. So you need a sensitive gamma ray detectors to see these sources.
Okay. Kostas? There is a Zoom question, sorry. So.
They just can unmute.
Yeah, please unmute yourself, Christoph.
Okay. I thought someone else was going to ask a question. Okay. So thank you very much for this talk. I enjoyed it a lot. I learned a lot. This morning we heard about photopion production and how to get like the 100 TeV ice cube neutrinos. You need PeV cosmic rays. So in the scenario that you modeled, are those PeV cosmic rays mostly from pevatrons that could also be in other galaxies, or like the secondary cosmic rays that you showed at the end? Because now thank you.
That's actually a very nice question. So in this case, we didn't consider the pevatrons inside the particular galaxies. We are mostly considering the cosmic rays, the cosmic ray population coming from jets from the center of the galaxy, the core of the galaxy cluster. So in this sense, we're considering a non-standard Milky Way or a historical, a past Milky Way when the center black hole is active. So we're essentially considering the active or a galaxy cluster, the cosmic rays are accelerated by the jets of the black hole at the very center of these galaxies. So the 100 TeV neutrinos would need 20 times, so about 20 PeV, about 2 PeV or higher. So that's already around the knee or even above the knee in our own galaxy. So another reason for that is you can already see in this plot where we compute our own Milky Way, the galactic neutrino flux, and you can see that's a very small fraction compared to the full sky neutrino flux. So this means the sources in our own galaxy is these PeV sources is energetic, but if you have a bigger like AGN's type of emission with a longer steady input of energy, that could dominate over these sources.
Thank you. So if we find cosmic neutrino sources.
Sorry. So we have one more question from the audience.
To ask concerning
when we go
concerning this model of acceleration in jets in galaxy clusters, why you need the jet to be in the galaxy cluster? Why cannot be like a radio galaxy jet? Or
we didn't really put, so the galaxy cluster model we used was essentially a intercluster medium gas distribution. And for the we added up a population of the galaxy clusters with a minimum mass of the cluster going down to 10 to the 12 solar mass, if I remember correctly, ish. So that's essentially the whole, and also using the mass halo function to summing over the contribution from different mass groups of the galaxy cluster. Does that answer your question, or?
I don't know. So it is because in the galaxy cluster you have more matter density for targets than in the intracluster medium, or so
yes.
Why the jet has to be into the, okay.
Yes, and also the sources, the active galactic nuclei, the jets are constantly found in the cores of a galaxy cluster. So it's more like the jets are already there. So this is what the galaxy cluster observation, you commonly see those AGN jets in the past history, or the current cores of the galaxy cluster. So that's why we consider this scenario. So essentially traditional models of the AGN would only look at the emission from the jet itself, but we just think of a second order, not second order, but something slightly different, which is not only the jet, but look at the environment surrounding the jet and see how that would impact the secondary emission.